Okay, let's consider these examples. We have three loops here. Loop 1, all of them are identical with a width of W and a height of L. Now, loop 1 is being pulled from the left into a region where I have a magnetic field, B, that's in blue, pointing perpendicular to the page towards us. So it's being pulled from the left, where there is no magnetic field, into this region. Loop 2 is being moved towards the bottom in the region where we have a magnetic field. And loop 3 is being pulled from the top, where we have no magnetic field, towards the bottom, where we have a magnetic field. Now, the question is, which loop has the greatest induced EMF at the instant shown? We start with loop 2, it's the easiest. Loop 2, there is no change in magnetic field as we move it, let's say from there to here. Since there is no change in magnetic field and no change in the area of the loop, the flux is not going to change. So if the flux is not going to change, the EMF in loop 2 at the instant shown is 0. Now, for loop 1, if I'm going to show it just a slight instant later, so instead of having, let's use in the diagram here, 1, 2, 3, 4 field lines in it, the number of field lines now in it, in the new color at the new position, is double. 1, 2, 3, 4, 5, 6, 7, 8. Now, if I'm going to move loop 3 this, at the same velocity, I'm going to need to duplicate this distance, but towards the bottom here. So that would be the distance. Now, the original flux in loop 3 is due to 1, 2, 3, 4, 5, 6 field lines. The new flux is 8. So for loop 1, we changed from 4 to 8. For loop 3, we changed from 6 to 8. So the one that resulted in a bigger change in flux is loop 1. So if it is a bigger change in flux, it means a bigger induced EMF for the same amount of time. Let's consider this question here. In this case, we have a loop. Let me change the color here. I'm not sure it is very visible. Okay, we have a loop perpendicular to the screen with its normal pointing towards the right, parallel to the magnetic field. So the magnetic flux in this case is BA. The angle between B and the normal is 0. So if we cut the magnetic field in half, the new flux is going to be BA over 2. If we use, let's call this B2 and this B1, so it's going to be B1A over 2. Now the question is asking if we want to create a second magnetic field to oppose the change in flux, what would be the direction of that second magnetic field? Now here, what happened to the flux? It decreased from BA, B1A, to B1A over 2. To oppose the change in flux, I need a magnetic field that's going to supplement this flux here. So I need a magnetic field in the same direction of B1 or B2. Okay, let's consider the situation. We have a solenoid here where we have a current that's applied to the solenoid that's flowing in the direction here shown through these arrows. That results in a north pole on top and a south pole on top. A south pole in the bottom. And we position a loop on top of the solenoid just perpendicular to the north pole of the solenoid. Now the question is, as we increase the current in the solenoid, what direction will the induced current in the ring be? What direction will current be induced in the ring? Okay. Is it in the same direction as the solenoid, opposite to the solenoid, or no current? Okay, let's work this out. So when we increase the current in the solenoid, what's that going to do? That's going to increase the magnetic field due to the solenoid. Remember, the magnetic field due to the solenoid is given by this expression, mu0 n I. Increase I, you increase B. N is the number of coils per unit length, and mu0 is a constant. Now, increase in I is going to increase B, which means that's going to increase the flux through the ring. So the flux through the ring is going to increase. It's going to increase in what direction? It's going to increase with a magnetic field pointing upwards. Now, what we have learned from Faraday and Lenz's law is that the induced EMF is going to be such that it's going to oppose that increase in flux. In other words, the flux due to the induced current is going to be opposite to this flux. So the flux due to the induced current, if I use color here, should be such that the magnetic field due to the induced current is going to be like this. For the magnetic field to be like that, now, using the right-hand rule, the current has to be, okay, remember here you are thinking of inside the loop, so your fingers should be going into the loop in that direction. So for them to go into the loop, it should point this way. So my current is going in the clockwise direction here. And thinking about the poles due to the ring, if the magnetic field is pointing down, that means I'm going to have a north pole in the bottom and a south pole on the top. That's due to the induced current. In this case, we have a current in the loop, I forgot to draw it, that's flowing in this direction. If the current is flowing in this direction, that means, using the right-hand rule again, thumb is in this direction, fingers wrapped around the wire, so my magnetic field due to this current is pointing up. In other words, this is my north pole due to this ring, and this is my south pole. The question is, which way is the magnet moving if it is inducing a current in the loop in the direction shown that I just showed? Is it moving up or down? Now, the current here is resulting in a flux that's pointing in the upward direction. The north pole, due to the permanent magnet, would result in a flux in the loop pointing in the downward direction. So let me draw it in red, what's due to the magnet. So the flux due to the, in yellow, the flux due to the magnet is pointing in this direction. The flux due to the loop is pointing in this direction. Now, if the magnet is moving down, that means it's going to increase this yellow flux. And as we see here, the red flux is opposing that increase, which means that that's actually what's happening. The magnet is moving down. If the magnet was moving up, then the yellow flux is going to be decreasing. If the yellow flux would be decreasing, the induced EMF would be such that it's going to oppose that increase. So instead of having the red arrows up, we'll have the red arrows down, and the current will be in the opposite direction. Now, this is an interesting question. What if I reduce the resistance in the wire? Will the magnet fall faster, slower, or at the same speed? In other words, will it matter? Now, the equation that we have was giving us the EMF. It's minus change in flux over time. Now, the current in the wire is going to be EMF over R, using Ohm's law. Now, the larger the current, the larger the red magnetic field that's induced due to that current. The larger that magnetic field, the bigger is the force that's going to oppose the downward motion of the magnet. So in other words, if we reduce the resistance, we get the magnet to move slower. Why? Because we have a bigger current resulting in a bigger induced magnetic field. Okay, let's consider this question here. We have a flat coil. We are given the area. We are given its resistance. We are told at time t0 it is oriented, so its perpendicular normal makes an angle 0 relative to a magnetic field of 0.12 Tesla. And we are told that the loop is rotated to an angle of 30 degrees in 0.5 seconds. And we are asked to find the induced EMF. Okay? So now, what you need to remember is the EMF is equal to minus delta phi over delta t. Our delta t is given in this question, 0.5 seconds. Our delta phi is going to be phi final. What's phi final? It's going to be BA cosine of phi. In this case, it's going to be BA cosine of 30 degrees. My phi initial is BA cosine of phi, but in this case phi is 0, so it is just BA. Phi initial is B, which is 0.12 Tesla times 0.2 meters squared. So it's going to be 0.024 Webers. My phi final is going to be the same quantity times cosine of 30 degrees. And cosine of 30 degrees is 0.87. So it is 0.87 times that. So we get 0.021 Webers. And my EMF is then minus 0.021 Webers minus 0.024 Webers over 0.5 seconds. So that gives us an EMF of minus 6.4 millivolts. Now, what is the direction of the induced current? Okay, so what happened here? If I redraw the initial condition, this was my loop and the magnetic field was perpendicular to it. Final condition is what's shown here. That's resulting in a smaller magnetic flux, as you notice it here from your equations. Now, to oppose a change in magnetic flux, remember that the change here is a reduction in the magnetic flux. The induced current should produce a magnetic field in the same direction as the original magnetic field. To result in a direction in the same direction, to result in a magnetic field in the same direction, using the right-hand rule, the current has to be in this direction. Okay, we have a different situation here. We have a solenoid and we have a ring, a loop, inside that solenoid. And we have several questions. First, what happens to the flux through the loop when we increase the area of the solenoid? Increasing the area of the solenoid is not going to change anything, because remember, the magnetic field inside the solenoid is given by mu0 n I. That does not depend on the area of the solenoid. Okay, now the next question. What happens to the flux through the loop when we increase the area of the loop? Flux through the loop is BA cosine of phi, but cosine of phi is 1, so it's just BA. If I increase the area, I increase the flux. B is still given by this. So when we increase the area of the loop, we increase the flux. So first answer, no change. Second answer, increase the flux. Now what if we increase the current in the solenoid? If we increase the current in the solenoid, we increase B. If we increase B, that increases the flux. So that increases. Now, what if we rotate the loop slightly? If we rotate the loop slightly, then my phi is BA cosine of phi, or as it is written here. Cosine of phi is going to be smaller than 1. So that means I have a decrease in the flux. Okay, now we have the opposite situation. We have the loop, a large loop, and a solenoid inside. And the question is, what happens to the flux through the loop when we increase the area of the solenoid? Okay, when we increase the area of the solenoid, we increase the area where we have a magnetic field. So the flux is going to increase. What about if we increase the area of the loop, not the area of the solenoid, like having a bigger loop like this? The area of the magnetic field is going to still remain this bluish color here. So when we write the flux as BA, A is that area there, and that does not change. So increasing the area of the loop does not change the flux in this case. What about if we increase the current in the solenoid? If we increase the current in the solenoid, we increase that B. If we increase B, then we increase the flux through the loop. Okay, we have two situations here in which is the induced current up. In the first case, B is in and V is towards the right. In the second case, B is out, in and towards us, and V is towards the left. Let's use the right-hand rule. In the first case, thumb is towards the right, fingers are perpendicular to the screen into the screen, so positive charges are being pushed up. So in that case, the current is up. Let's check the second case. V is towards the left, so thumb is towards the left. B, the magnetic field, is out, so it's towards us. So again, the force on positive charges is up. So in both cases, we have a current in the upward direction. Okay, let's consider these other questions. So we have a wire carrying a current I, a long straight wire, and I have a ring next to it. They are telling us that the current in the wire is increasing, and we are asked to figure out the direction of the induced current in the loop. Okay, remember, due to the current in the wire, we have a magnetic field. The magnetic field is given by mu0 I over 2 pi r. The direction of that magnetic field, using the right-hand rule, thumb is up, we wrap the fingers around the wire, so it's going to be this way and this side, into the page and that side. So the magnetic field in the region where I have the loop is pointing perpendicular to the page, out of the page. So I'm drawing it through these points. Of course, it's stronger towards here than here, but that does not matter. Its direction is that way. Now, we are increasing the current, meaning we are increasing the flux in this direction. The induced current should be such that it's going to oppose that increase. To oppose that increase, the magnetic field due to the current should be in that direction. To have a magnetic field in that direction, the current, using the right-hand rule again, the current should be in this direction, which is clockwise. Let's have another example. In this case, the current in the wire is decreasing. What is the direction of the induced current? Using the right-hand rule again, the magnetic field due to the wire, thumb is down, wrapping the fingers around the wire, so it is into the page here. So it's into the page where we are interested really. It's into the page, so and it's going to be out of the page on this side. Okay. It's given again by the equation mu0 I over 2 pi r. R is the distance away from the wire. Now we are told that the current in the wire is decreasing, not increasing. If it is decreasing, what does that mean? It means that this flux is going to become smaller. So the induced current should be such that it's going to oppose the change in flux. So it's going to oppose the decrease in this flux. To oppose it, the magnetic field due to the wire is going to be in that direction. Going in that direction, using the right-hand rule again, so it's going to be like this. It's clockwise. Okay, we have another question. the current in the large wire loop is counterclockwise. So we have a current that's counterclockwise and increasing. The question is, what is the direction of the induced current in the smaller loop? Now, because of that current, using the right-hand rule, we have a magnetic field due to that current that's inside the loop. That's what we are concerned. Inside the loop is going to be pointing out. Okay, and since that current is increasing, that flux is increasing. So the small loop should have a current to oppose that increase. To oppose that increase, the magnetic field due to the small loop is going to point into the page. If it's going to point into the page, again using the right-hand rule, my current is going to be this way, in the clockwise direction. Now here the situation is different. The current in the large loop is counterclockwise, like the previous case, and increasing. What is the direction of the induced current? We are going to use the right-hand rule again. Remember here we have figured out that inside the loop the magnetic field is out of the page, perpendicular to the page. Now outside the loop the story is different. The magnetic field here is, due to the large loop, is in this direction. So inside is like this, outside it is out. I mean into the page. Now here, because that current is increasing, it means this magnetic field inside the smaller loop is increasing. It means the flux in that direction is increasing. So due to Lenz's law, the magnetic field due to the current induced in the loop should be in this direction. For the magnetic field to be in that direction, the current has to be in this direction. So counterclockwise.